Okay, good morning. So like we said, Shaun sent out an email. You guys have a test. So you have a test on Friday, November 27th. Okay, during class time, of course. During class time. And Shaun will invigilate it. So it's, of course, it's Shaun's test. So yeah, you guys are getting kind of a weird experience. But you're still in Shaun's course. I'm just the mouthpiece, so to speak. And so Shaun will invigilate. Shaun will invigilate the test. Okay. And I will say that if you have any questions about the test, you're better off asking Shaun. So any questions, go to Shaun. But of course, if you have questions about what we covered in class, then maybe it's easier for me to answer. So just depends on, you know, your question. Contact Shaun if you have any questions. You too, Onkar. How about there? I always have to tell it to mute participants when they come in, even though that should be default. I don't know, it's really weird. Contact Shaun if you have any questions. Okay. There was an email where he said what sections it would be on. Let me just, here, I'm gonna just go have a look because I got the email too. Okay. The email says 1.5. So sections 1.5, all of chapter 2 covered. And 3.1, which was what we're gonna finish today, just in a little bit here. Okay, so I don't know, we did more in chapter 1. I picked up at 1.8, I think. So I don't know, maybe he's not testing you guys on inequalities and stuff. That's nice of him. Way nicer than me. So let's see here. Let's do a little bit of review. Unless there are, do you guys have questions about this test? So there was a message. Say that again.
Makes sense to me.
Cool. Awesome. All right. So just some quick review. We talked about quadratics. So quadratic functions. Okay. To graph quadratic functions, so that's something like ax squared plus bx plus c, right? That's a quadratic when the highest power or the degree of the polynomial is 2, right? And so if we have a quadratic, to graph it, the easiest way to graph it is if we put it into standard form. The easiest way to graph a quadratic is to put it into standard form by completing the square. By completing the square. Oops. Okay. which is, so if this is f of x, and then we have f of x, function of x is a, which is the same a as from up here, right? A times x squared, oh sorry, not x squared, I'm just doing the same thing over again. X minus h squared plus k, okay? Where the vertex is at hk, okay? Notice that it's minus h, so h, if it's plus 2, for example here, x plus 2, h would be minus 2 or negative 2. And then the k is just stolen from the standard form. So the vertex tells us, so the vertex, remember, is either the maximum if it's facing down, right? So if you have a parabola that looks like this, here, this is the vertex. Or if you have something like this, right? Depending on if it's facing down or facing up, the vertex is either a maximum or a minimum, right? What? Maximum, minimum. Okay, so this is if a is less than 0, the vertex is a maximum, and if a is greater than 0, right, pointing up, then the vertex is a minimum. So we can learn a lot from just the original equation, right? So here's the general form of this quadratic, and we know that a is the same for each of these, and the a determines if we're facing up or facing down. So we can learn a lot from this function, even from the general form, but it's going to be, once we have the vertex, right, that tells us what the maximum or what the minimum is. So I think that's kind of what we got to last day. Let me just make sure. Standard form, blah, 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 blah. And then, of course, I'll add, so these have been sort of bullets. The y-intercept, right? Or let's start with the x-intercepts because they're harder. So the x-intercept is where f of x equals 0, right? So solve for x. Those are where y equals 0. That's your x-intercept. And once you have it in standard form and you know where the vertex is and you know if it's pointing up, for example, if you end up with this type of situation, right, you're not expecting to find any x-intercepts. So you would go through the motions, you would maybe use, you could set f of x equal to 0 here, you have a, you have h, and you have k, so then you can just solve for x. You'll find that you'll probably take the square root of a negative, which can't happen, right? And so then you would conclude, okay, there is no x-intercept. The y-intercept is where x is 0. Is where x equals 0. So depending on, you know, what you prefer, you can either use x equals 0 in here and solve for f of x, or you could use the original equation. I always like to think of it as you put a lot of work into putting it into standard form, so why not use the standard form? Sometimes you might want to use the original just to make sure that you're on the right track. But you can always confirm all your work using Desmos. Okay, so to finish off the section, we'll do 2 word problems. So modeling using quadratic functions. Using quadratic functions. Okay. So the first example, I don't know how he chose these names, but I mean, works for me. Rex wants to build a fence for his dog, Chico. Cute. Rex wants to build a fence. Oops. Build a fence. Oh, that doesn't really read like fence, does it? Fence for his dog, Chico. He has 100 meters of fencing. Okay. This is a pretty classic problem, right? So we have some restrictions on how much fencing we have, and then how can we maximize the area, right? And so this problem comes up over and over and over again. And so it's good to have seen it. So he has 100 meters of fencing. What are the dimensions of the fence with the largest area he could build? So what are the dimensions? Oops. What are the dimensions of the fence with the largest area he could build? And what is the maximum area, right? And so we're talking about the dimensions, right? That's the width and the length. But what's the actual area of it so we can calculate it? Or what you'll see is our work will give it to us. What is the maximum area? If you think about it, right, the area is going to depend on the dimensions, right? So what we're going to do is a function depends on x. So a function f depends on x, right? And so here we're going to let our area be the y, the output, and then the dimensions, or one of the sides, the lengths of one of the sides, is what we're going to use as our input, our x. Okay. So what we know, right, and you can kind of map it out, but we know we only have 100 meters of fencing. Oops. So if we have something, so some sort of area here, right? The fencing is going to be the perimeter, right? And so if we let this be x and this be y, then this length must be x and this length must be y. Okay. I am assuming that I'm going to make some sort of rectangular shape. Okay. But we can assume that. We're allowed to. So what that means is that y plus x plus y plus x must be 100, right? I don't want to use 90 or something weird, right? I want to maximize everything. So I have 100 meters of fencing. And so we say 100 must be x plus y plus x plus y, which is 2x plus 2y, right? So what I can do, so 100 must be 2x plus 2y. Now what I'm going to do, because I don't want to deal with x and y, I'm going to solve for y here and figure out what y is in terms of x. Find y in terms of x, right? Because if I know what x is, so if I say x is going to be 10, well, that's 10, 20, and then the remainder has to be split between the y's, right? So if I know x, then I also know y. Okay, so that's what I'm going to do here. I'm going to solve for y. So 100 minus 2x is 2y. And so y, and here I do this quite often. I always like to have what I'm solving for on the left-hand side, but just remember your equal sign is just a revolving door, right? So as long as you don't change anything, you're allowed to just kind of swing it around. And I manipulate it at the same time, which can be confusing, right? But just kind of study it and make sure it makes sense. So 100 minus 2x, right? I just moved this side over here, this side over here, but I also am gonna divide now the right-hand side by 2. So y is gonna be 50 minus x. Okay. So the area here, right? How do we find the area? We assume that you know how to find the area. It's going to be x times y, right? That gives us our area here. Area is x times y. I just found y in terms of x. So now I can set up the function for the area. So a of x is x times y, which is x times 50 minus x. Okay, I can expand this out, and so I get 50x minus x squared. Because this is a quadratic now, the highest power of x is 2, I'm going to write this as a quadratic, so I'm going to move or with decreasing powers, which is typically how we write polynomials anyways. Negative x squared plus 50x. Okay. So now, this is a quadratic function. Quadratic function. Notice the negative, right? This tells us, okay, so if a is the coefficient of x squared, then a must be -1. So a is -1, so it's pointing down, right? So here, oops, a is less than 0, so pointing down. Okay, which means the vertex is going to be a maximum, right? So we can put this into standard form, right? Write a of x in standard form by completing the square. So what do I have to do? I have to get x squared plus something x on its own, right? So I have to pull out anything in front. So I have to pull out that common a, which is just -1 in this case. So a of x is negative, and then x squared minus 50x. Okay, so you're pulling out the negative, which means when you put it back in, negative x squared plus 50x, we have to keep it the same, right? So now I have it in the format where I can manipulate it to become a perfect square. What I have to do, right, if you look at the notes from last day, right, I have to add b over 2 squared and then subtract b over 2 squared. Okay, so add b over 2 squared and subtract, right? We're basically adding 0 by adding it and subtracting it immediately. Okay. B in this case is going to be the -50, right? So it's a different b from the general form. So what we have is we have minus x squared minus 50x plus -50 over 2 squared minus -50 over 2 squared. And there's nothing on the outside, so that's good. But just remember, this negative is multiplying everything here. Okay, negative 50 over 2 squared. Okay, never mind. We're not quite there yet, because what I want to do, right, this is a perfect square. That's what we forced to happen. So what we have, right, we can rewrite this as negative x and then rats. Plus, is it plus or is it minus? I have to look at my notes from last day. Completing the square. Here. Okay, so I've made this happen. I forced that. Okay, so then it is x plus, but b over 2, so it's not squared anymore. So that's why it's going to be minus, and then squared. Okay. X plus, oops, plus negative 50 over 2, then squared. Oops. Okay. You know what? One more set of brackets. Minus negative 50 over 2 squared. Square brackets. Okay, keep track of your brackets. So this brackets, or this set of brackets is just blocking off the negative 50 over 2. This set of brackets is blocking off our perfect square. And then this set of brackets, again, is keeping our negative 50 over 2 on its own. And then this square set of brackets is keeping this negative on the outside. So if I have to remove these, then I have to move this negative inside, for example. Okay. Now I can simplify negative 50 over 2, which should just be negative 25. So I have negative, and I'm not going to have any fractions anymore, so I have x minus 25 squared minus, and now I've got negative 50 over 2, okay? Negative 50 divided by 2 is negative 25, but then I'm going to square that. 625. So minus 625. Okay. If I have to write this in standard form, right? Standard form, remember, is a times x minus h squared plus k. So I have to expand this negative 1 inside. So I have negative x minus 25 squared plus 625. And what you can do is you can graph this in Desmos. You can graph both the first function and the function that you just found. Make sure that they're the same, right? That's how you can check your work. So now we have the vertex. The vertex is going to be at h is 25 and k is 625. Okay. We already decided, right, this thing is pointing down, which we would see here as well, right? We've got this negative, so now the vertex is the maximum. So it's at 25, 625. Let's just pretend that we've drawn it here at 25, 625. That's the vertex, and it might look something like this. We can put in some work and we can find the x and the y intercepts, right? We're not going to do that for this problem because all we're asked to find is what are the maximum dimensions. So remember here on the y-axis we have a of x, which is the area, and on the x-axis we just have x. Okay. So the maximum here is when x is 25. And the area when x is 25 is 625. Okay. So therefore, the area is maximized to 625, I'll say meters squared, right? Areas. I'm not too picky about units. I don't know if Shaun doesn't really have, oh, he does have units in here. So I don't know how picky he is, but if you remember, that's great. But really, the area is maximized at 625. When x is 25, so, okay, so we know x, so let's go back to our original graph, right? Now I'm letting x be 25, so 25, 25, and just remember, y is 50 minus x, so we have to solve for y as well. It's gonna be 25 again, right? So y is 50 minus x, so y must be 50 minus 25, so y is also 25. The maximum dimensions is 25 by 25. And I'll put meters on there just in case. Yeah. Good. So that's one type of problem. Another common type of problem is what we call a profit function. And so profit functions are sometimes quadratics. And what's nice about profit functions is it lets us answer things like, what's my maximum profit? How much do I need to produce or sell to make that profit? That kind of thing. Okay, so so for another example, suppose a dog bone company, or any company, a dog bone company has a profit function of P of X, okay? So here, this is the profit. Oops. P of X is negative 0.002 x squared plus 4x minus 1,600. Okay, the profit is in dollars or some sort of monetary unit. And so here we're going to be talking about dollars as the output, and x is going to be how many dog bones. Well, it's not obvious, but if you're working at a dog bone company, presumably you're selling dog bones. And so here, this is x is your dog bones, or your x. Okay. The profit that you make depends on how many dog bones you sell, right? So we can ask things like, what is the maximum profit? What is the maximum profit? How many dog bones need to be sold? I'll add to maximize the profit. To maximize the profit. Okay. I can already tell that my coefficient on x squared is negative, so it's going to be pointing down, right? And so what I'm going to say here, this is just my thought process. Since a is less than 0, we're going to have something like P of x is your y value, and x is here, and we might have something that looks like this. Okay, so the vertex is the the maximum, right? So we're really just asked to find the maximum, right? The vertex, which means all we have to do, right? Because the vertex gives us the x, so that's the number of dog bones, and p of x, which is the profit, the maximized profit here. So really all we need to do is we need to find the vertex, okay? I'll put it in green here. Oh. Need to find the vertex, okay? All right, so what that means is we have to put this thing into standard form. So remember, standard form, we have to pull out a common factor of a, so we have to pull out negative 0.002 from 4, okay? So what I'm gonna do is I'm gonna start at this original profit function, p of x is negative 0.002 x squared plus 4x minus 1,600. And I'll move this over, give myself some room. So first thing I need to do is I need to factor out this a. So I get negative 0.002 times x squared, okay? I'm only gonna pull it out from the x's, right? The x squared and the x, and then I'm gonna bump this minus 1,600 to the outside, okay? I'm allowed to do that. Things, make sure after each step that nothing has changed. Right. So 4 divided by negative 0.002, use your calculator, 4 divided by negative 0.002 puts me at negative 2,000 x, bracket minus 1,600. Okay. Now I have something that I can put into a perfect square. So I'm gonna add b over 2 squared and subtract b over 2 squared, where b is negative 2,000. Okay, so it's gonna be quite a large number. So we have negative 0.002 on the outside, and then x squared minus 2,000, oops, almost missed a 0. That would mess up our calculations, wouldn't it? 2,000x plus negative 2,000 divided by 2 squared minus negative 2,000 divided by 2 squared. Uh-oh. Now I've done it, haven't I? I need to make some room here. Okay. I always want to stack it. You should be stacking your equal signs, but I write too big in the beginning is often my problem. So I have the luxury of moving things over, but you should be stacking your equal signs. Okay. So I have plus something minus the same thing. I'm adding 0 technically, right? That's all times this negative 0.002. And then on the outside, I've got minus 1,600. Okay. So now I can make this a perfect square. Okay. So I get negative 0.002 times x plus negative 2,000 over 2 squared. Okay. All right. So these brackets are keeping our perfect square together, but I've also got the negative 0.002 on the outside. So minus negative 2,000 divided by 2 squared minus 1,600. Okay. It's not until I have this that I'm going to simplify, right? Because I want to see that plus b over 2, or at least for my sake, I find it hard if I have simplified already. Negative 0.002 times x minus 1,000 squared, right? Negative 2,000 divided by 2 is 1,000. And then minus 1,000 squared. Okay, so negative 2,000 divided by 2 is still negative 1,000. Negative 1,000 to the power of 2 puts me at 1, 2, 3, 4, 5, 6, 7, a million. So minus 1 million. Okay. Minus 1,600. To collect these constants, right, I need to bring in, or I need to expand this negative 0.002 inside, right? And so what I get is I get negative 0.002 times x minus 1,000 squared. And then I have negative 1 million divided by negative 0.002. I don't know why I divided. It should be multiplied. It's clearly multiplying. I don't know why I did that. Times negative, I'm going to backtrack. And then times negative 0.002. 2,000, that makes more sense. So plus 2,000 minus 1,600. So finally, 0.002 times x minus 1,000 squared. And then plus 2,000 minus 1,600, so plus 400. Okay, here h is going to be 1,000, right? Because it's x minus h, so h is going to be the positive, and k is going to be 400 because it's plus 400. So therefore the vertex is at HK, which is 1,400. Okay. X is the number of dog bones we decided, and Y is the profit. Okay. So the maximum profit is $400, which happens when we sell 1,000 dog bones. Oops. Which happens, hey, when we sell 1,000 dog bones. Okay. I've got a page break here, so I'm going to put it at the top of the page, otherwise I'd leave some space. At what volume of dog bones, so how many dog bones would we need to sell if we're making zero profit, right? So here we've sold 1,000 dog bones and we've made $400. Remember, that's the maximum. And so at zero profit, Y is 0, right? So at what volume of dog bones would they make 0 profit? No profit, let's say. Okay. This is essentially saying P of X must be 0, solve for X, which is the X-intercepts. Okay. So if we have P of X in standard form, we just found it to be negative 0.002 times X minus 1,000 squared plus 400. I'm going to force P of X to be 0 and solve for X. Equals negative 0.002 times X minus 1,000 squared plus 400. Order of operation says I have to subtract 400 first, then divide. Okay, so minus 400 is negative 0.002 times x minus 1,000 squared. Negative 400 divided by negative 0.002, negative 400 divided by negative 0.002 is 1, 2, 3, 4, 5 zeros. Oh, it should be 200,000. There. Which is x minus 1,000 squared. Okay, so I can take the square root of 200,000. Is x minus 1,000. So solving for x, again, I'm going to use that revolving door. First, I'm going to see if I get any nice number when I take the square root of 200,000. I don't. So I'm actually just going to leave it as the square root of 200,000 for a little bit. X is going to be the square root of 200,000 plus 1,000. Only the 200,000 is, oh, whoops. What did I forget? Not just the square root, the positive and the negative of the square root. Whoops. There. That's important. Because if you think about your quadratic, right, we need to have two x-intercepts if there are any x-intercepts. And so that's where we get them from, right? When we take the square root, we actually get the positive and the negative version because they'll both give us the positive x squared. Okay, so x is going to be negative 200,000, or let's do maybe the positive first, plus 1,000. So the profit is 1,447.213596. It is money, so we can round it to 2 decimal places and not feel bad, but we should keep 2 decimal places. And then negative square root of 200,000, 1, 2, 3, and then plus 1,000 is 552.7864,045. So what happens is the profit is zero if they sell 2.79. You can't sell 0.79 of a dog bone, but just to keep it kind of as close to this number as possible, I am doing the decimals because we don't need to think about it that much. So the profit is zero if they sell 552.79 dog bones, right, or 553. Or if they sell 1,447.21 dog bones, or 1,447. Should be 47, they're still making a little bit of profit, right? Because what happens here is we've got our P of X and we've got our X. Well, if we found our vertex was at 1,400. So 1,400 is maybe here. No, extend this. So what we're finding is that here at 1447 and here at 552, okay, These are the x-intercepts. Oops. Ooh. Should be even, but notice that here you make a negative profit. So until you make 552, let's say 553 dog bones, or sell 553 dog bones, you're not making a profit, right? You've got fixed expenses that you need to cover. And then here you start making a profit. Here you make a profit. And then after 1,447 dog bones, you actually lose money, right? So you want to stop production here. Okay, so here in this region, we make a profit. And then here, you have negative profit. So you're losing money. So that's kind of a tricky problem, right? We think that if you just keep selling stuff, then you'll just make infinite profit, but that's not true, because the cost of producing this many, right, after some point exceeds the benefit, right? So it exceeds the profit. And so you want to find your maximized profit. And I forgot a bracket here. And so you want to hit this sweet spot of 1,000 dog bones and you make a profit of 400. Okay. I guess that's it for us. Are there any questions? So that's the end of chapter 3. So here, this is the end of chapter 3, right? Kind of, we just ducked in and out, and we will start chapter 4 next day.
Okay, I've got a quick question.
Yeah.
For most real-world applications, if we were to do like something like this, would we expect to see the A portion be a negative number?
Yeah, so the profit function, this is a particular case of a monopoly, I'm pretty sure. So, which is like a special case in the market. But then you would, so they typically have these quadratics as a profit function. A profit function can be anything though. So this is kind of a special case and kind of a fun one to work with.
I'm just trying to, what's what I'm looking for? I'm trying to think of where would we see a similar function like this, except A is greater than 0.
So if it's pointing up, where would we see it? Could you have a profit function?
Or is it like a minimum value? And this would be we're searching for.
So then what you would be finding is the minimum value. Well, so what if you wanted to minimize the amount of time you spent, right?
Okay.
That kind of thing. So it just depends on what you're talking. Do you want to minimize something or do you want to maximize something?
Okay, yeah, that makes sense. Okay.
Cool.
Awesome.
Yeah, it depends on the scenario, but yeah, awesome question.
And we're seeing you Monday.
I'll be here.
All right.
Have a good weekend, you guys.
You too. Ciao.